Alright, this is the last presentation in this course as planned and prepared for summer 2012. Let's see what we can do. We're going to talk about quadratic residues, which are basically perfect squares, only in modulo p arithmetic. So again, something very natural if we're thinking about trying to haul everything we know from regular arithmetic over to arithmetic modulo a prime number. We will talk about square roots in modular arithmetic, and then we are going to spend some time on quadratic reciprocity, which basically involves laws that allow us to determine when a number actually is a perfect square modulo p. Alright, let's go. So, the underlying definition for the whole presentation is that if we have a and m being natural numbers, then a is a quadratic residue of m if and only if the greatest common divisor of a and m is 1, and there is an integer x, so that x squared is equivalent to a modulo m. So that equivalence here, that congruence, basically just says that a is a perfect square only in a wraparound arithmetic. Otherwise, well, when that not happens, a is called a quadratic non-residue of m. And as an example, well, if we want to find all the quadratic residues of 13, well, as long as the number is small, basically all we do is we simply square all the numbers from 1 through 12 in this case, because 13 is prime, so every number between 1 and 12 has greatest common divisor 1 with 13, and so what do we get? Well, compute the residues. We obtain, well, 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared is 16, which ends up being 3. 5 squared is 25, which ends up being 12. 6 squared is 36, which ends up being negative 3, ends up being 10. 7 squared is 49, which ends up being 10, also modulo 13. 8 squared is 64, which is minus 1, which is again 12. 9 squared is 81, 7 should be 3. We were at 9 squared. 10 squared is 100, and that is 9 off from 91, which is 7 times 13, so that should be 9. 11 squared is 121, which it should be plus 4, because it's 4 off from 117. And 12 squared is 144, which is 130 plus 13 plus 1, so that should be 1. Alright, so nothing to it. As long as the numbers are small, right? We see some of the stuff is doubled up, and in fact we're going to show that all the quadratic residues do occur exactly twice, at least when we go modulo a prime number. And if we sort them right, well, then we get 1, 3, 4, 9, 10, and 12 as the quadratic residues modulo 13. So those are all the perfect squares in modulo 13 arithmetic. Alright, well, first lemma. If we've got an odd prime and a is so that p does not divide a, then the congruence x squared congruent to a modulo p has no solutions or exactly 2 solutions. And how do we prove that? Well, we've got an earlier theorem that says that the congruence has a solution if and only if a raised to the phi of p divided by the greatest common divisor of 2 and phi of p equivalent 1, if and only if that is equivalent to 1 modulo p. And moreover, that same theorem says that if there are solutions, there are exactly greatest common divisor of 2 and phi of p solutions. Greatest common divisor of 2 and phi of p is the greatest common divisor of 2 and p minus 1, and that is 2. And then I just have to conclude the sentence in grammatically correct fashion. There are 2 solutions that are incongruent modulo p if there are any solutions at all. Okay. So that can now be used to show that when p is an odd prime number, then there are exactly p minus 1 over 2 quadratic residues of p in the set from 1 through p minus 1. And the way that goes is, well, we know that there are p minus 1 numbers in the set from 1 to p minus 1. And if 2 of them have equal squares, then it is exactly these 2 that share a particular quadratic residue, right? Because from the previous lemma, we have seen that the equation x squared equivalent to a has either 2 solutions or no solutions. So if any 2 of them collapse into the same square, then it isn't possible for more of them to collapse into the same square. And that means there are at least p minus 1 over 2 quadratic residues of p in the set 1 through p minus 1, because the worst thing that could happen is if one of them pairs up, it pairs up with exactly one other number and no more. So that means we divide at most by 2, but by the same token, actually, there cannot be more distinct quadratic residues, because if we had even one more quadratic residue, then one of these congruences would have exactly one solution, and that was prevented by the previous lemma also. So I'm not sure if I should have said that briefer. Basically, they all pair up and that's it. And that's what the theorem says. Okay, so now if we have a prime number and we have a primitive root of p, and if a is so that p does not divide a, well, then a is a quadratic residue of p if and only if the index of a modulo r is even. And well, if we go in one direction, if the index of a modulo r is even, well, then a is r to the index of a modulo r, and that is r to the index of a modulo r divided by 2 squared, and now because the index is even, this is an integer. And well, that means therefore then that a is a quadratic residue of p. Going in the other direction, if a is a quadratic residue of p, well, then there is an x, so that x squared is equivalent to a modulo p. And that means that 2 times the index of x modulo r is equivalent to the index of a modulo r, and the whole thing is modulo phi of p. And so because phi of p is even, the index of a must be even. That bothered me for a minute when I just looked at the slides before the presentation. Well, what was it? An equation, number times variable equals right-hand side modulo sum modulus, has a solution if and only if the number, if and only if the greatest common divisor of the number and the modulus divides the right-hand side. Greatest common divisor of 2 and phi of p is 2, and that is so because phi of p is p minus 1 is even, and that then means that the index must be even also, because undoubtedly the index of a modulo r is the solution of this equation. Okay, so we move on, and we are coming to the entity that pretty much plays center stage for the remainder of this presentation, and that is the Legendre symbol. So if we have an odd prime and a is an integer, so that p does not divide a, we divide the Legendre symbol of a over p as, well, Legendre symbol of a over p being 1 if a is a quadratic residue of p, and it's negative 1 if a is a quadratic non-residue of p. So those of you who have done some things in measure theory or in statistics realize this is very similar to an indicator function. The positive indicator again is 1, and unlike indicator functions in analysis, the negative indicator actually is a negative 1, and we will see that that makes a good number of formulas just work a lot better than if we would have said 0 if it's quadratic non-residue. All right. So for example, if we're looking at the Legendre symbols for a equals 1 through 12, modulo 13, what are they? Well, the Legendre symbol for 1 I didn't write down, and that's because, well, it is quite obvious, right? 1 is a quadratic residue. Yeah, there's not much else to be said. So the first one that we actually have to deal with is 2, and actually what I'm going to do here, I think, is that I'm going to use the fact, I'm going to use the fact that 2 is actually, oh my goodness, right now words fail me. It's one of those numbers that rotate through everything. So I'm going to look at all the numbers, all the powers of 2, and see what's going to happen. And so one of the things that you can work out for yourself is that 2 is a quadratic non-residue, and as soon as we know that, we realize that 2 squared is a quadratic residue. We know that 2 cubed is a quadratic non-residue. We know that 2 to the 4th is a quadratic residue, and 2 to the 4th is 16, which ends up being 3 modulo 13. 2 to the 5th is a quadratic non-residue, and that is because 2 to the 5th is 32, and it's 6 because 2 to the 5th is 32, which is 6 modulo 13. 2 to the 6th is a quadratic residue, and that's because it's 64, which is negative 1, which is 12, so I get a 12 here. 2 to the 7th, again, is a quadratic non-residue. Well, what is 2 to the 7th? 2 to the 7th is 128, and 128 is modulo 13 is negative 2, which is plus 11 modulo 13, right? We're looking at 2 to the 9th, and 2 to the 9th is, no, 2 to the 8th. 2 to the 8th is 256, and 256 is negative 4 modulo 13, which is 9, right? And it's because the exponent is even, it is a quadratic residue. And what I meant to say here is, of course, 2 is, oh great, I mean, the numbers are currently just falling into and out of my brain. Hang on just a minute here, this is annoying. Yeah, what I meant to say here was that 2 is a primitive root. And by now we're that far through that we're also seeing that from here, right? Because the powers of 2 have not wrapped around yet. And we are with the 8th power. Well, the 9th power is 512, and if we're looking at modulo 13, we're realizing that the next multiple of 13 is 390 is 520, so it's negative 8, so it ought to be plus 5 modulo 13. And because the exponent is odd, it is a quadratic non-residue. 2 to the 10th is 1024, and 1024 ends up being 10 modulo 13, and that is a quadratic residue. Let's see, why is 1024 10 modulo 13? Because if I subtract 10 from 1024, I end up with 1014. And let's see, so you divide 101 by 13, you end up with 10, and then you've got 114, and you divide that, and you just end up with a, yeah, because you've got 104, you end up with a remainder of 10. Okay, look, you can work out the rest of the numbers with a calculator. I'm pretty sure that's what I have done here also. 2 to the 11 ends up being 7 modulo 13, and it's a quadratic non-residue. And 2 to the 12th actually ends up being 1 modulo 13, and that ends up being a quadratic residue. And that actually you wouldn't have needed a calculator anymore. We know that 2 is a primitive root, so 2 must rotate through everything, and the last one has to be 1 modulo 13, which means this one had to be 7. Okay, so we can talk our way through that if/when we have a primitive root. But of course, as p gets large, all these computations get more demanding. Finding primitive roots can get hard, and so what we want is, we will ultimately want to find ways to determine whether something is a quadratic residue that are a little bit faster. And Euler's criterion is a first step towards that, because if p is an odd prime number and a is an integer so that p does not divide a, then the Legendre symbol of a over p is equivalent to a to the p minus 1 over 2 modulo p. And the proof, even though at first it looks kind of strange, is actually very simple. We will prove that a to the p minus 1 over 2 is equivalent to 1 modulo p when a is a quadratic residue, and we will prove that it's equal to negative 1 modulo p when it's a quadratic non-residue. Okay, so let a be a quadratic residue. Well, then there is an x, so that x squared is equivalent to a modulo p. And that means that a to the p minus 1 over 2 is x squared to the p minus 1 over 2, which is x to the p minus 1, which, by Fermat's little theorem, is 1 modulo p. And if a is a quadratic non-residue, then the congruence x squared equivalent to a modulo p has no solution. And, well, now we have to argue a little bit. So because a has a multiplicative inverse modulo p, for every y between 1 and p minus 1 inclusively in both cases, there's a zy, and that zy is just y inverse a, so that y times zy is equal to a. And because x squared equivalent to a modulo p has no solution, we have that this y and this zy that gets it back to a, those two are not equivalent. So that means we can pair the numbers in the set 1 through p minus 1 so that the product of each pair is a. And that means that a to the p minus 1 over 2 is nothing but p minus 1 factorial, because if I now, for every one of these p minus 1 over 2 powers, take the a and replace it with exactly one of these pairs here until all these pairs are exhausted, I end up with the product of the first p minus 1 integers, and that's p minus 1 factorial. And that is equivalent to -1 modulo p by Wilson's theorem. And so that finishes Euler's criterion. All right, as an example, well, for p equals 31 and a equals 2, we have that the Legendre symbol of 2 over 31 is 2 to the 31 minus 1 over 2, which is 2 to the 15th, and that's equivalent to 1 modulo 31, because 2 to the 5th is 32, and 32 is equivalent to 1 modulo 31, so we end up with just 1 to the 3rd, right? 2 to the 5th to the 3rd, modulo 31, and that ends up being 1. Okay, so as long as we can do fast modular exponentiation, these things do work out rather nicely, but again, for the remainder of this presentation, we'll find all sorts of formulas for this Legendre symbol. So for example, our next theorem here is if we have an odd prime number and a and b are integers so that p does not divide a and p does not divide b, we want to know a little bit about how the Legendre symbols connect to each other. And so for example, when a is equivalent to b modulo p, then Legendre symbol of a over p is equal to the Legendre symbol of b over p. When without any further hypotheses, the product of the Legendre symbols of a over p and b over p is the Legendre symbol of a times b over p, and the Legendre symbol of a squared over p is equal to 1. Yeah, that should directly follow from 2, and it will. So, proof. Of course, we'll use Euler's criterion, and we can do that because for Legendre symbols, which are always either spitting out plus or minus 1, equivalence modulo p is the same as equality. We always know that equality implies equivalence modulo p, but if something has only two possible values, as long as those two values aren't the same modulo p, equivalence modulo p will imply equality, and that's the case here. Okay, so that means when a is equivalent to b modulo p, then Legendre symbol of a over p is a to the p minus 1 over 2 modulo p. But because a is equivalent to b modulo p, that means that it's b to the p minus 1 over 2 modulo p, which is Legendre symbol of b over p modulo p. For the product, Legendre symbol of a over p times Legendre symbol of b over p, well, that's equivalent to a to the p minus 1 over 2, b to the p minus 1 over 2, which is ab to the p minus 1 over 2, which is the Legendre symbol of ab over p modulo p throughout. And finally, a squared over p, the Legendre symbol of that is, of course, the product of the Legendre symbol of a over p times the Legendre symbol of a over p. And if you take two numbers that are either both 1 or both -1 and multiply them together, you get 1, and that's it. Okay, so that now tells us that for certain numbers we can do some direct computations. So for example, -1 is a quadratic residue modulo p when p is equivalent to 1 modulo 4, and it's a quadratic non-residue modulo p when p is equivalent to -1 modulo 4, as long as p is an odd prime number. And the proof, well, when p is equivalent to 1 modulo 4, then p minus 1 over 2 is even, and by Euler's criterion that means that the Legendre symbol of -1 over p is -1 to the p minus 1 over 2, which ends up being 1 because we've got an even exponent. And yeah, this equivalence is of course modulo p, but then as said before, it's equivalent modulo p, then it's going to be equal overall as long as the right hand side ends up being 1 or -1. And when p equals equivalent -1 modulo 4, well then p minus 1 over 2 is odd, and that means the same computation will this time show that the Legendre symbol of -1 over p is -1, because this time we'll have an odd exponent in there. Okay, so Gauss's lemma now to compute, to determine whether something is a quadratic residue says the following. we take an odd prime number and we let a be an integer, and we want that to be so that p does not divide a, and we let s be the number of least positive residues modulo p of the numbers a, 2a, 3a, all the way to p minus 1 over 2a that are greater than p over 2. And Gauss's lemma says that that means that the Legendre symbol of a over p is -1 to the s. Now that looks like we are making things actually worse, but note that the name is Gauss's lemma, not Gauss's theorem. We're going to use Gauss's lemma to ultimately prove the law of quadratic reciprocity, which appears to be fairly central in this area. And so this is something that will be helpful to just put things in a different light. The direct computational value is, as far as I can see, and again, I'm not an expert on this, but to me the direct computational value looks like it's less than Euler's criterion, which is fairly nice and computational. Okay, what do we do? Well, let's take a look at the least positive residues modulo p of these numbers. And we're simply going to say that u1 through us, where this is exactly this s, those are the ones that are greater than p over 2. And v1 through vt, we let that be the ones that are smaller than p over 2. Well then, because p is a prime number, a has a multiplicative inverse modulo p, and that means that no two of the numbers a, 2a, 3a, all the way to p minus 1 over 2a are congruent modulo p, because that would mean that two of the numbers between 1 and p minus 1 over 2 would be congruent after canceling the a. So that means that s plus t is p minus 1 over 2, meaning none of these numbers, no two of these numbers are equivalent. Now we want to do a little bit more because we want to sort the u's back in with the v's, and the one way to do that is to subtract them off of p, because if you subtract something that is greater than p halves off of p, you end up with something that is less than p minus 1 over 2. And so I should have p over 2a here, and I should have p over 2 times a here. Let me finish that real quick. Let me fix that real quick. Well, sorry about the interruption and the mistake. This should be a p over 2, and that should also be p over 2, because we're still doing arithmetic modulo p, of course. Okay, so we do continue here. Yes, we do. And let's see, the p over 2, I'm currently just, as I'm always also encouraging my listeners, of course, I'm trying to think all the way through. P over 2 is not even, so we can really also work with greater than and smaller than. So everything really is in order here. All right, well, we just try to keep working through with comprehension as we should. Okay, so if I take something that is greater than p over 2 and subtract it off of p, I end up with something that is smaller than p over 2, which means I end up between 1 and p minus 1 over 2. And that's exactly what I want to do, because we're going to see here that there will be no crashes. So if we had p minus uj is equivalent to vj modulo p, well then if I say that uj is kja and vi is kia, because remember they're all among these numbers here, well then I would have that after bringing the uj over, I would have kja plus kia is equivalent to p, which is equivalent to 0 modulo p. And that's not possible, because after canceling the a, I realized that ki plus kj is greater or equal than 2 and smaller than p, and none of those numbers is equivalent to 0 modulo p. All right, so that means the vi and the p minus uj, they are pairwise distinct. No two vi are the same, no two uj are the same, and no vi is equal to a p minus uj. And they're all in 1 through p minus 1 over 2. That means that because we have also p minus 1 over 2 of these guys overall, that the set 1 through p minus 1 over 2 is in fact the set p minus u1 all the way through p minus us, and then we have v1 through vt here. Hence, and now this is one of those setups where we're only seeing it in advance afterwards, why this is going to work. I take -1 to the s, a to the p minus 1 over 2, p minus 1 over 2 factorial. Well, that's the product of -1 to the s of the product j equals 1 to p minus 1 over 2 j times a. Well, that's because the factorial is the product of the j's, and the a to the p minus 1 over 2. If I put one of these a's into every factor, I get exactly the j's there. But we do know that modulo p, the set of the j's, is equal to the set of the ui's and the vt's. And so this is negative 1 to the s, product j equals 1 to s, uj, product I equals 1 to t, vi, not vt. And we're back. Yeah, that's the product of the vi's. Well, now I can put the negative sign in with the uj's, right? So that's the same as the product of the negative uj's times the vi's. And of course, then modulo p again, the negative uj is the same as p minus uj. But now I know that this product, of course, by what we had just shown up here, is just p minus 1 over 2 factorial. And look, that's the same as this p minus 1 over 2 factorial here. So this equivalence modulo p now, I can turn, after canceling the p minus 1 over 2 factorial, into negative 1 to the s. A to the p minus 1 over 2 is equivalent to 1 modulo p. And that means that the Legendre symbol of a over p is equivalent to a to the p minus 1 over 2, which is equivalent to negative 1 to the s modulo p. And we continue, and here's another one. If we have an odd prime number, we can say exactly when 2 is a perfect square modulo p, because the Legendre symbol of 2 over p is negative 1 to the p squared minus 1 over 8. So this is something where you can now decide very quickly whether 2 is a perfect square modulo p, because you just figure out whether p squared minus 1 is divisible by 8, which is something you can figure out from the last few digits of p squared minus 1. And then whether it's even or odd, so you figure out whether it's divisible by 16, I guess. And once you have that, you know whether 2 is a perfect square modulo p or not. Okay, so proof. We certainly apply Gauss' lemma here. And, well, what do we know? We look at the integers 2j. And the integer 2j is less than p over 2 as long as j is between 1 and greatest integer below p over 4. And it is greater than p over 2, but still less than p for greatest integer below p over 4 being strictly smaller than j, being less than or equal than p minus 1 over 2. And so that means that the Legendre symbol of 2 over p is equivalent to negative 1 to the p minus 1 over 2 minus greatest integer below p over 4. And that is, again, modulo p. Well, that's perfectly fine. And, well, the rest of the proof is now simply rewriting the exponent in simpler form. And because the base is negative 1, powers will be equal if and only if their exponents are equivalent modulo 2. So what we're going to do now from here on out, for this result at least, will be modulo 2. First note that the function f of n equals n minus 1 minus greatest integer below n over 4 has period 8 modulo 2. And that is because, well, we just compute f of n plus 8. And that's n minus 1 plus 8 over 2 minus n plus 8 over 4 greatest integer below that. Well, that'll be n minus 1 over 2 plus 8 over 2, which is 4, minus n over 4 greatest integer below n over 4, minus 2 here. And of course, those are 0 modulo 2, so this is just n minus 1 over 2 minus greatest integer below n over 4. And that is an equivalence modulo 2, and that's what we wanted to prove here, right? Because that's f of n. Similarly, the function g of n equals n squared minus 1 over 8 has period 8 modulo 2, and that's because g of n plus 8 is n plus 8 squared minus 1 over 8. When you work that out, you end up with n squared minus 1 over 8, and then you also have 2 times 8 times n over 8, which is 2n, and you've got 64 over 8, which is 8, and that's, of course, n squared minus 1 over 2, when n squared minus 1 over 8, as we're going modulo 2. So g of n plus 8 is also equal to g of n. And that means the result is proved if we can show that the left side, negative 1 to the n minus 1 over 2 minus n over 4, is equivalent to negative 1, is equal to negative 1 to the n squared minus 1 over 8 for n equals 1, 3, 5, and 7. And that is actually not hard, so let's go ahead and do it real quick. For n equals 1, we get an exponent 0 here, we get an exponent 0 here, so that works. For n equals 3, we get an exponent 3 minus 1 over 2 is 1, minus 0, so we get an exponent 1 on the left, and we get 9 minus 1 over 8, which is 1, same exponent on the right. For n equals 5, we get 5 minus 1 over 2, 4 over 2 is 2, minus 1 is 1. And we get 25 minus 1 is 24 over 8 is 3, so we get negative 1 to the first, negative 1 to the third. That's the same thing on both sides. And for 7, we get 7 minus 1 is 6, divided by 2 is 3, minus 7 over 4, greatest integer below. 3 minus 1 is 2, whereas 7 squared is 49, minus 1 is 48, divided by 8 is 6, so we get negative 1 to an even exponent on both sides. So we get that worked out, and therefore the result now holds by induction, right? It holds for the first 4, and after that it repeats modulo 8 in the odd numbers. Okay, for example now, if we are looking for the Legendre symbol of 5 modulo 23, well, we don't necessarily want to do the modular exponentiation, and so Legendre symbol of 5 over 23, well, 5 is negative 18 over 23, and whereas 5 doesn't have any factors because it's a prime number, or any factors we're speaking of because it's a prime number, 18 certainly does. So this is negative, the Legendre symbol of negative 1 over 23 times the Legendre symbol of 2 over 23 times the Legendre symbol of 3 over 23 times the Legendre symbol of 3 over 23, because 3 times 3 is 9, times 2 is 18, times negative 1 is the negative 18. And that, of course, is now just negative 1 times negative 1 to the 23 squared minus 1 over 8. And, of course, here we're just squaring, so that goes away. And that gives us negative 1 times negative 1 to the 23 squared is 529, minus 1 is 528. 528 over 8 ends up being 66, because it's 480 plus 48. And that means that the whole thing is negative 1. Okay, good. Let's talk briefly about what we can do with modular square roots when we have them. Turns ultimately out that we can do something like a fair electronic coin flip. Before we get there, let's take a look at p, q being two distinct odd prime numbers. We set n equals p times q, and we want a element n be so that a and n have greatest common divisor 1, and so that x squared equivalent to a modulo n has a solution. Then x squared equivalent to a modulo n has 4 distinct solutions. Well, we already had a result that said it has either 0 or exactly 2 solutions, but remember that was modulo a prime number. So now we're looking at something that is a product of exactly 2 distinct prime numbers, and it makes sense that it ought to go to 4 solution by Chinese remainder theorem, which we're also going to use here. So, because x squared equivalent to a modulo n has a solution, so do the congruences x squared equivalent a modulo p and y squared equivalent to a modulo q. If x is a solution of x squared equivalent to a modulo p, then p minus x, which is not equal to x modulo p, and yeah, first of all, it's not equivalent to x modulo p because it's got to have 2 solutions, and this negative x solves x squared equivalent to a modulo p also, so p minus x is essentially the second solution there. And moreover, because x squared minus z squared is x plus z times x minus z, these are the only solutions, because if I ever had 2 solutions, then p would have to divide this product, which means it would have to divide either the sum or the difference, so the numbers really are either equal or negatives of each other. I think I'm just rehashing one of the earlier proofs there a little bit, but we might as well. The same argument shows that y squared equivalent to a modulo 2 has 2 solutions, and those are y and q minus y, and we're going to use that a little bit later on, that these solutions are exactly that. And if we use all possible pairings and the Chinese remainder theorem, we obtain exactly 4 solutions for the congruence x squared equivalent to a modulo n, namely all the possible pairings of x and p minus x with y and q minus y. Okay. Quick result that says that we can also sometimes compute these square roots. So if p and q in the natural numbers are distinct odd prime numbers, so that p and q are both equivalent to 3 modulo 4, and if a is so that the greatest common divisor of a and n is 1, and x squared is equivalent to a modulo n has a solution, well then x, so that x is equivalent to a to the p plus 1 over 4 modulo p, and x is equivalent to q plus 1 over 4 modulo q, that x solves x squared equivalent to a modulo n. And the reason why we need the equivalence to 3 modulo 4 is to make sure that this exponent here is an integer in each case. Okay, so we simply note that a to the p plus 1 over 4, which is a number in modular arithmetic because we've got an integer exponent here, when we square that, we end up with a to the p plus 1 over 2, and that's a to the p minus 1 over 2 times a, which is Legendre symbol of a over p times a, which is equal to a. Yeah. And that's modulo p. And we can do the same thing for q, and that means that then by Chinese remainder theorem, things will work out. Okay, so that leads us to this idea of a fair electronic coin flip. How could that go? Well, ultimately we have to remember that technically a coin flip is nothing but any game of chance in which each player has exactly a 50% chance to win, and the main thing to then set that up fairly, electronically or otherwise, is to make sure that there really is a 50% chance. So here is how this could be done electronically. So we want to develop that so that it can be played electronically and so that each side can verify who won and without a possibility to cheat. Okay, so I play against you and I pick two distinct large prime numbers, p equivalent to q equivalent to 3 modulo 4. That means when I send you n equals pq, okay, and I send you n equals pq, and you will win if you can factor in. So of course I need to set this up in such a way that p times q is hard to factor. I guess that also makes sense in games of chance where you are certainly not encouraged to trust anybody. You shouldn't basically you shouldn't play poker with an open hand, right? Okay, so if what you will do then is you will pick an x between 1 and n and send me x squared. Of course you don't tell me x. Same story. I don't show you my hand, you don't show me your hand. You send me a equals x squared modulo n. Now, because I know the factorization, I can find the fourth square roots x, y, n minus x, and n minus y, and I will send you one of them. All right? And now, if I send you x or n minus x, well, then you already know the number, and the number doesn't help you factor anything. But if I send you y or n minus y, then by adding y or adding what I send you or n minus what I send you, you end up with p. You potentially could get p, and then you could factor things. So there's a 50% chance that I pick x or n minus x, because I don't know which of the four numbers is the number or n minus the number that you chose. And if I pick that, then the number remains hard to factor for you because I haven't given you any new information. But there's also a 50% chance that I pick y or n minus y, and in which case we will have that x plus y, greatest common divisor of x plus y with n is q, or x plus n minus y, greatest common divisor with n is p. You can work that out from the previous theorems, and in that case you can quickly factor in. Okay, so that is the fair coin flip. If you follow the procedure, you realize that at no point in time, unless somebody gives something away, did either chance have the opportunity to give something away. And at the end of the story, you either tell me what the factors are, or you say I can't factor it, and then of course I would have to disclose what n was so you can verify that I didn't throw you a random number or so. But either way, this would be a fair electronic coin flip. Okay, so now we are coming to, as I already said, this is the last presentation in the course as planned, so we're coming to the last highlight of this course, and that is the law of quadratic reciprocity, which is a way to turn the Legendre symbol p over q for prime numbers, for odd prime numbers, into the Legendre symbol of q over p, at least in the form in which we've written it. Okay, so we take p to be an odd prime number in this lemma, and we let a be an integer, an odd integer, and so that p does not divide a. I set T of A and P to be the sum j equals 1 to P minus 1 over 2 of the greatest integer below ja over P. Then we claim here that the Legendre symbol of A over P is negative 1 raised to the T of AP. So that obviously is a lemma, because this is something that looks and is very technical, but we will need it for a proof of the law of quadratic reciprocity. So, proof. Well, we'll show that this TAP is equivalent modulo 2 to this exponent S from Gauss's lemma. So basically, we now go as exactly as in the proof of Gauss's lemma. We consider the least positive residues of A, 2A, all the way through P minus 1 over 2A modulo P. We let U1 through US be those that are greater than P over 2. Remember, we really need P over 2, not P over 2 times A. And we let V1 through VT be those that are smaller than P over 2. And, well, what do we get? If we take JA, if I take any of these numbers here, and I divide it by P, then we get a quotient, and the quotient is very easily expressed. It's JA over P, greatest integer below that, so that's where you can sort of get the idea that that's what the TAP should be. And a remainder, well, the remainder is the least positive residue, so it's one of the UI or VI. And so that means, if we also recall from the proof of Gauss's lemma that the numbers from 1 through P minus 1 over 2 are exactly the set P minus U1 through P minus US union V1 through Vt, where the two sets are disjoint and have S elements and T elements respectively, we get the following. If I take the sum j equals 1 to P minus 1 over 2 of the JAs, then by doing the division by P, I get that JA is P, greatest common divisor JA over P, not greatest common divisor, it's P, greatest integer below JA over P, plus U or V, as is in each case appropriate. And if I sum that all up, I get that it is the sum of all the P, greatest integer below JA over P, plus the sum of the UJs plus the sum of the VJs, because all these remainders are distinct and they are exactly the UJs and VTs here in the earlier numbers. Okay, so with the other thing that we get is that this is the sum j equals 1 to P minus 1 over 2, or that the sum j equals 1 to P minus 1 over 2 is the sum j equals 1 to S P minus Uj plus sum j equals 1 to T Vt. And that sum, of course, is just S times P minus the sum of the Uj plus the sum of the Vt. We can see here now that this sum is here, this sum is here. Here's where we're getting an S, so we're getting a lot of stuff that we certainly would like. And so now we just add the first line and this broken second line here. We get the sum of the JAs minus the sum of the J's. Okay, we subtract, not add. So this one minus that one on the left is this one minus that one on the right. So we get that this is the sum of the PJA over P minus PS. Sum UJ minus sum UJ is 2 times the sum of the UJ. Sum VT minus sum VT is 0. And of course, those should be i's here, just like on the other slide. Let me fix that real quick. Okay, yeah, sorry about that typo. What we have, therefore, is this equation, and we're just going to haul that over to the next panel. Here is the same equation as from the previous panel. And if we're looking at modulo 2, well, yeah, okay, first we're going to pull things together a little bit. If I factor out an a here, I get a minus 1 times the sum of the j's is equivalent to, if I pull out, is equal to, if I pull out the p, I end up with the remaining sum being t of AP. That's how t of AP came into being, presumably. And then we've got the PS and 2 times the sum of the UJs. And now we're going modulo 2, because now we see, remember, we demanded that A was odd. And so that means A minus 1 is even, and that means this left side is equivalent to 0 modulo 2. P is odd, so that means that P is equivalent to 1 modulo 2. That also means that S is equivalent to, that PS is equivalent to S modulo 2, and 2 is equivalent to 0 modulo 2. So we're just ending up with TAP minus S is equivalent to 0. And that, of course, means that TAP is S modulo 2. And that's what we wanted to prove, because that means that negative 1 to the S is negative 1 to the TAP, and that means negative 1 to the TAP is the Legendre symbol of A over P. Okay, so now we look at the law of quadratic reciprocity. We take P and Q, distinct odd prime numbers. That should say B here. Well, let's make sure it does. All right, now it says B. More importantly, when we've got these two distinct odd prime numbers P and Q, then the Legendre symbol of Q over P times the Legendre symbol of P over Q is actually negative 1 to the P minus 1 over 2 times Q minus 1 over 2. And, well, how do we do that? Well, we consider the pairs of integers x, y with 1 smaller equal x smaller equal P minus 1 over 2 and 1 smaller equal y smaller equal Q minus 1 over 2, and we realize that there are exactly P minus 1 over 2 times Q minus 1 over 2 of them. So that is that exponent up here. And now, suppose for a contradiction that for one of those pairs x and y, we have that py is equal to qx. Well, then q divides py, and that means that q divides y. But because y is between 1 and q minus 1 over 2, that's not possible. And that means that py is not equal to qx for all of the xy that we have under consideration here. And so now we can therefore distinguish them, those pairs xy, into pairs xy where py is smaller than qx and py where py is greater than qx. Well, when py is smaller than qx, that happens if and only if x satisfies the one constraint that it has, which is that it's between 1 and p minus 1 over 2. And y would have to be so that it's greater or equal than 1, because that's this constraint here, but it can at most be the greatest integer below qx over p, because if I multiply anything greater than this by p, I would end up with something that is greater than qx. Hence, there are some x equals 1 to p minus 1 over 2 of greatest integer below qx over p points xy, so that x is between 1 and p minus 1 over 2, y is between 1 and q minus 1 over 2, and so that py is smaller than qx. And the symmetric argument shows that there are y equals 1 to q minus 1 over 2 greatest integer below py over q points xy, so that x is between 1 and p minus 1 over 2, y is between 1 and q minus 1 over 2, and py is greater than qx, because what we would do there is we would let y run from 1 through q minus 1 over 2, and we would have to have that x is less than or equal to py over q greatest integer below that, because otherwise if I multiply x with q, I would violate this inequality. Okay, so that means that p minus 1 over 2 times q minus 1 over 2 is the sum x equals 1 to p minus 1 over 2 greatest integer below qx over p, plus the sum y equals 1 to q minus 1 over 2 greatest integer below py over q. But of course now these are those t's that we just had before, right? That's tqp plus tpq, and that means that the Legendre symbol of q over p times the Legendre symbol of p over q is negative 1 to tqp times negative 1 to tpq, which is negative 1 to tqp plus tpq, which is negative 1 to p minus 1 over 2 times q minus 1 over 2. And that is the proof of the law of quadratic reciprocity in this form. It turns out that the law of quadratic reciprocity has another form. So this theorem actually turns out to be equivalent to the preceding theorem. We're not going to show the equivalence. We are just going to prove that this result also holds. And if you are interested in the converse, it is a nice, if you're interested in proving the preceding form of the law of quadratic reciprocity from this one, that is a good exercise. So we take an odd prime number and we let a be odd so that p does not divide a. And if q then is another odd prime number so that p is equivalent to plus minus q modulo 4a, then the Legendre symbol of a over p is equal to the Legendre symbol of a over q, which means that the property that a is a perfect square modulo p only depends on the modulus of the prime number in question modulo 4a. Okay, the proof will first focus on odd prime numbers a, and we'll distinguish these two cases, plus or minus q, and the rest comes out of the prime factorization. So let's take a look at this. Take a to be an odd prime number, and we're going to consider the case that p is negative q plus 4a times k, or 4ka. And when we have that, we can look at the product of the Legendre symbol of a over p and the Legendre symbol of a over q. And if I can show that this product is equal to 1, then I could just multiply both sides with the Legendre symbol of a over q to get the desired equation. Okay, so the Legendre symbol of a over p is negative 1 to the p minus 1 over 2 times Legendre symbol of p over a, and the Legendre symbol of a over q is negative 1 to the q minus 1 over 2 times a minus 1 over 2 times the Legendre symbol of q over a, by the first form of the law of quadratic reciprocity that we already have proved, and via the same argument I can just multiply both sides with Legendre symbol p over a or Legendre symbol q over a. Well, now we are going to use, of course, what we know about p and q. And, well, what do we know? Well, first of all, we combine the exponents here, and that's, of course, that we add the exponents. The a minus 1 over 2 is a common factor. P minus 1 over 2 plus q minus 1 over 2 is p plus q minus 2 over 2. The Legendre symbols multiply together, so that's the Legendre symbol pq over a. And now p plus q, well, p plus q is 4ka, right? So that means that this is negative 1 to 4ka minus 2 over 2, which is 2ka minus 1 times a minus 1 over 2 times the Legendre symbol pq over a. And because 2ka minus 1 is an odd number, that is, of course, then negative 1 to the a minus 1 over 2. And remember, p is negative q plus 4ka, so q is also negative p plus 4ka, and so we end up with p times negative p plus 4ka here. And we realize that this number up here, when we multiply it out, it's negative p squared plus a multiple of a, which means these two are equivalent modulo a, and that means I can drop off the stuff that I've added, and so this is just negative 1 to the a minus 1 over 2 negative p squared over a, Legendre symbol of that. And that is negative 1 to the a minus 1 over 2 negative 1 over a, Legendre symbol, and the Legendre symbol of p squared over a. Well, that ends up being negative 1 to the a minus 1 over 2 negative 1 to the a minus 1 over 2 times 1, which just is 1. In the other case, at least as long as a is an odd prime number, is the case that p is equal to q plus q plus 4ka. That one's a little bit quicker, because again, I look at Legendre symbol a over p, Legendre symbol a over q. That is, as before, negative 1 to the p minus 1 over 2, a minus 1 over 2, negative 1 to the q minus 1 over 2, a minus 1 over 2, Legendre symbol p over a, Legendre symbol q over a. I combine the Legendre symbols to get the Legendre symbol p times q over a, and I realize that whether I raise negative 1 to q minus 1 or 1 minus q gives me the same thing. And now, of course, I combine again just as before. So a minus 1 over 2 factors out of the exponents. P minus 1 over 2 plus 1 minus q over 2 gives us p minus q. And it should be p minus q over 2 here. And now it is p minus q over 2. So p minus q over 2, a minus 1 over 2 here. I replace the q with p plus 4ka. Okay, whether that's plus or minus doesn't really matter too much, and I could have just renamed the k, so let's keep that as is, and we move on. Well, p minus q over 2 would be 4ka over 2, which is 2ka, and we realize now, because a minus 1 over 2, because a is odd, that's an integer already, so this is an even exponent, and this power will go away, and we get p squared, Legendre symbol of p squared over a, because again it's p squared plus a multiple of a, so this is equivalent modulo a to p squared. So we end up with 1 times 1, which is 1. And finally, when a is an odd number, you just use the prime factorization on the equation, and you end up with the result. Okay, final thing that we're going to talk about is Pepin's test. I hope that's how the gentleman is pronounced, but it looks very much like a French name to me. And it is, again, a primality test, and it's a primality test for prime numbers, for Fermat numbers. So the primality test for prime numbers, yeah, fantastic. Okay, the Fermat number f sub m is 2 to the 2 to the m plus 1, and that thing is prime if and only if 3 to the fm minus 1 over 2 is equivalent to 1 modulo fm. How do we do that? Well, for the right to left direction, we assume that 3 to the fm minus 1 over 2 is equivalent to 1 modulo fm. Well, that means that 3 to the 2 to the 2m minus 1, take the Fermat number, this plus 1 with this minus 1 goes away, so I end up with 2 to the 2 to the m, divided by 2 is 2 to the 2 to the m minus 1, so that's all correct. That thing is equivalent to negative 1 modulo fm. Well, we also then know, because if we just square that, we end up with 3 to the 2 to the 2 to the m. That thing is equivalent to 1 modulo fm, because negative 1 squared, which is a whole lot easier to say and to compute, is equal to 1. And now let's just have p be a prime that divides fm. So let's just assume basically that fm has a prime factor. Well, then we know that the order of 3 modulo p divides 2 to the 2 to the m, because if this is valid modulo fm, then it is also valid modulo p. Well, so that means that the order of 3 modulo p is a power of 2, because after all these things, there are no factors other than 2's, and plenty of them. And because 3 to the 2 to the 2 to the m minus 1 is equivalent to negative 1 modulo p, we conclude that the order must be exactly 2 to the 2 to the m, because, of course, if the order was smaller, then any further squaring would just lead to 1's and not to negative 1's. And we remember that 2 to the 2 to the m is fm minus 1. That means that fm minus 1 is the order of 3 modulo p, which must divide p minus 1. That means that fm minus 1 is less than or equal than p minus 1. That means fm is less than or equal than p, and that means that fm is equal to p, and that means that fm is prime. Conversely, for the other direction, we assume that the Fermat number 2 to the 2 to the m plus 1 is prime. Well, 2 to the 2 to the n plus 1, completely different line of thought for just a minute. 2 to the 2 to the n plus 1 minus 1, well, that's 2 to the 2 times 2 to the n minus 1, and that's 2 to the 2 to the n squared minus 1, which is 2 to the 2 to the n minus 1 times 2 to the 2 to the n plus 1. Well, that factorization implies via an easy induction that 3 divides fm minus 2 for all m, because basically if 3 divides the difference between the nth Fermat number minus 2, which is 2 to the n minus 1, and the n plus first Fermat number minus 2, which is 2 to the n plus 2 to the 2 to the n plus 2, 2 to the 2 to the n plus 1 minus 1. That means that divisibility by 3 is passed on from one Fermat number to the next one, and if I take 5 minus 2, I get 3, which is divisible by it, so one of the first Fermat numbers does it. Well, that means that Fermat numbers are equivalent to 2 modulo 3. And that is what we're going to use, because that will tell us now that 3 to the fm minus 1 over 2, that is equivalent to Legendre symbol of 3 over fm. But that's, of course, rough to compute. Modulo fm, if it's prime. Well, that is by law of quadratic reciprocity, negative 1 to the 3 minus 1 over 2, fm minus 1 over 2, Legendre symbol of fm over 3. And here's where we realize that, well, 3 minus 1 over 2 is 1. fm minus 1 is 2 to the 2 to the m over 2, so this is going to be 1 ultimately. And fm, as we've just seen, is equivalent to 2 modulo 3, which means this is just the Legendre symbol 2 over 3, and that ends up being -1 by direct computation. You just check the numbers. 1 squared is 1, 2 squared is 4, which is 1 modulo 3 also, which means that 2 is not a perfect square. It's not a quadratic residue modulo 3. And that was Pepin's test. That was the last thing that we did here. And in some ways, this ending is, well, I personally like it in some ways because I like to end any part of my education on a note that says, hey, there is more. And basically, the law of quadratic reciprocity is something that is apparently quite widely used in certain parts of number theory. All we have seen is one test, and that is for primality of Fermat numbers. So there is apparently still a whole lot that can be done with the law of quadratic reciprocity. But one rule that I also will continue following in designing online setups for courses is I'm not going to stuff more into the course than I can do in a single term, and we will barely finish what we're doing here in the summer of 2012. So if you find further presentations by me on number theory, then I must have redesigned the course somehow, and if you get a syllabus, hopefully then the rearrangement will also be visible here. Let me say that I certainly have learned a lesson here because number theory was not my specialty, and pretty much the second half of the course I learned along with you. I'm afraid that sometimes showed a little bit in my hesitations and also in the errors on the slides. I certainly hope that that hasn't hindered or slowed you down, because typically we caught things, and there's something that mathematical authors also sometimes say with this: any remaining errors should be catchable by a sufficiently alert reader. It's like, yeah, thank you, brother. If I already knew this stuff, I wouldn't read the book. And similarly, if you already knew this stuff, you probably wouldn't take the course, but I hope it has worked for you. I can honestly tell you, I've enjoyed learning this, for me, new part of mathematics, and I hope that you have enjoyed it too. And if you really enjoy number theory, and if you want to go deeper, go ahead and do it. Read books and learn this stuff from the experts, because I can honestly say I think I've taken you as far as a non-expert can and should take you. With that, enjoy the rest of your career, literally.